Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. Previously we set up our pixel shader so that it can sample and use textures. Today we are going to add texture samplers to the low-level renderer and use them in the root signature. In addition, we'll send descriptor indices of the textures used in each material to the GPU so that the pixel shader can use them to fetch those textures. We can add a few predefined static sampler descriptions in the helper namespace, where we have other predefined structures such as rasterizer and blend states among others. I'll use the same pattern to define sampler states. The static sampler description has quite a few properties that can be configured. The filter determines how textures are sampled in different situations. For regular sampling, there are three cases that can be important for the resulting value. The minification is when the texture is on an object that is farther away, and therefore a pixel in screen space would overlap more than one pixel in texture space. Magnification is the other way around. When we render an object up close, one texel can cover more than one pixel in screen space. When the texture has MIP maps, we can sample from higher MIP levels to improve texture memory access as well as decrease flickering of pixel colors. The MIP part of the filter determines how samples from adjacent MIP levels are blended, if at all. As you can see here, we can set the filter type separately for minification, magnification, and MIP if we want to. We'll start simple and define a point sampler, a linear sampler, and an anisotropic sampler, all of them having the same filtering strategy for minification, magnification, and MIP maps. The address modes determine what value to return when the sample location is outside the range between 0 and 1. Address mode border will use a specific border color. For static samplers, it's only possible to use black, white, or transparent black colors. We can use any border color for dynamic samplers. Clamp will use the same color as the pixel that's just on the border of the UV range. Mirror will flip the texture around the U and V axis, and wrap will repeat the texture when the sample location is out of range. The address mode can be set separately for U and V directions. For 3D textures, we can also set it for the W direction. We'll set them to wrap, but we can change them anytime later. Please read this tutorial for more information about sampler filters, address modes, and other properties. MIP LOD bias will offset the sampled MIP level. For example, if the calculated MIP level to sample from is 3 and the MIP LOD bias is 2, MIP level 5 will be sampled instead of 3. Max anisotropy is only relevant when we use an anisotropic filter. The comparison function determines what function to use if you'd like to compare the sampled value against an existing value. This is useful, for example, when sampling from a shadow map, where we would like to test if the sampled value is less than the depth value of the scene. We are not using this yet, so we can set it to always, or never, or none. Min LOD and max LOD set a range for the MIP level to sample from. In general, we want to be able to sample from all MIP levels, so min LOD is 0 and max LOD is float max. We can also set the shader register, register space, and shader visibility, which we have to change later in order to specify to which register in the shader code the sampler state is attached, and by which shader stages it can be accessed. Now I can copy this 2 more times for linear and anisotropic samplers. I see that I accidentally selected the wrong filter, so let me pick the right one for this. Apart from the filter type, we can use the same configuration for all samplers. We might want to set max anisotropy to a higher value. It needs to be between 1 and 16, with the higher value yielding better quality at a greater cost. That's all we need for now. I'll just quickly add a helper function that makes it easier to set the shader register and visibility. Going back to where we create the root signature for opaque objects, we see that we already have the SRV indices root parameter in place. We only have to add the samplers. As I mentioned in the last video, we only need a linear sampler, but since we added all 3 sampler types for the purpose of demonstration, I'll add them as root parameters as well. To do this, we simply create an array of static sampler descriptions and set their shader registers. These should be the same as in our shader, where I forgot to set the correct register for the anisotropic sampler. This should be S2. We can include these samplers in our root signature easily by passing the pointer to this array and the number of samplers. Another advantage of using static samplers is that they don't take up any space in the root signature, as they are compiled directly into the shader when the pipeline state object is created. Okay, everything is set up for the shader side. Now we have to send these SRV indices to the GPU. We can do this using a constant buffer, but first we need to add new entries to our GPass cache. We need to know the total number of descriptor indices so that we can allocate enough space for them in the constant buffer. Then for each submesh in the scene, we have an array that contains the descriptor indices that are used for its material. So this is an array of arrays. Note that it's okay for materials to not use any textures, so this array could be empty. Of course, we do have to know how many indices are in each array. Therefore, we have another array for the number of textures per submesh. Finally, we need a pointer to the GPU buffer where we put the descriptor indices for each submesh. When we ask for the material cache, it should return the new arrays. Obviously, we have to update the material cache structure as well. When clearing the cache, we reset the total number of descriptors to 0. And we have to set the pointers within the cache buffer whenever it's resized, adding the new entries here as well. Don't forget to also update the position buffer pointer, otherwise you're in for a really confusing bug hunt. And the last pointer is for the SRV buffer pointers. At the end, we have to update the cache data size to account for the new cache entries. Now where we set the root parameters, if the material uses any textures, Then we can set its SRV indices buffer as a shader resource view to be accessed by the shader. The last step is to actually allocate a buffer and fill in the descriptor indices. In order to do that, we have to know how many indices we have to allocate for, if at all. We can add a new output parameter to getMaterials function that will yield the value we are looking for. In this function, we can fill in descriptor indices and the texture count per material. There is a subtlety here that's important to note. We are not copying an array for descriptor indices. We are simply setting a pointer to an already existing array which is part of the material memory block. And we sum over the texture counts for all materials to get the total number of descriptor indices. We can use this number to allocate a chunk of memory in the constant buffer and copy all indices into the buffer. To copy the indices, we loop through all items and check if they have any textures. First, the SRV indices buffer pointer is reset to 0. This is the GPU virtual address, which is a 64-bit unsigned integer. If there are any textures used for this item, their descriptor indices are copied to the buffer and the GPU virtual address to that part of the buffer is set in SRV indices. The SRV index offset is incremented by the number of textures so that we know where we should copy the next batch of indices. If we did everything correctly, our pixel shader should now have all information for texturing this model. All we have to do is to compile a shader variation that can handle textured materials. We wrote that part of the pixel shader in the previous video, and now we can enable it using conditional compilation. Right now we only have a compiled pixel shader for the default material which doesn't have any textures. So we need to add a second one. To make it a bit easier, I'm going to create an array of pointers to the compiled shaders. Then we can simply add the shader code after compilation like so. And then the shader group for pixel shader is just the first shader in the array. Now for the second shader, we have to define textured material so that it will enable that part of the shader. We can put this in extra args, which of course should be cleared before this point. And we can copy and paste this part where the shader is compiled and the one we sent to the engine is the second shader in the array. We do need to add a new shader ID. And we can remove the shader at shutdown. Next, we create a new material just for the fembot model. We'll use our new shader together with the array of textures to create the material. Note that the order of textures we are passing to this material should exactly match the indices we use here in order to sample from these textures. Again, we remove the material when we close the application. And finally, we can use this material to render the fembot model. It seems that I made a typo in the pixel shader. This should be sample. As you can see, the model appears to be darker now. That's because we are not passing the UV coordinates from the vertex shader. Here we see that the UV in the vertex shader output is set to 0, but we can simply use the UV member of the vertex element to set this value. Of course, we can't set this value for the shader variation of vertex elements without UVs. Okay, now we can see that the model is textured, but obviously something is not right. Most of the times when this happens, it's because the texture is flipped in the U or V directions. This means that there is a mismatch in the UV axis direction in DirectX and the 3D application that was used to create the UVs. This is fixed easily by flipping the axis. In our case, it's the V axis that's flipped. A better solution is to add a geometry import setting for this, which would flip any or both of the two axes. But at least for now, we can behold our first ever textured model in Primal Engine. As you can see, we also have the emissive parts. However, it looks a bit bland as it is. I'd like to emphasize it so that it has a bit more punch. One way of doing it is to magnify the emissive intensity depending on how close the view direction is to the surface normal. So we see more light emitted when we look at the surface dead-on. Let me go back to Visual Studio 2019. So if this is a textured material, we use the dot product of the view direction, which is defined up here, and the surface normal, and scale the result to our taste. Then we take the emissive color, square it, and multiply it by the result of the dot product raised to the power of 16. You can do anything you want with this emissive part since it's not physically based anyway. However, doing it this way creates the illusion that the emissive source is deeper within the volume of the model. After fixing my typo, we can see the result of the emissive calculation. Looking at the yellow and red parts, you can see how the light appears to come from within the model, creating some kind of translucent effect, where in reality there is none. Last thing we can play with is using the old rotator script which we still have here in order to make the model rotate. Though I'll slow it down a little. And here we can see the result of all our efforts so far. The model is textured and even uses the roughness value to make parts of it more shiny. One important aspect of texturing, however, is still missing, which is adding finer details to the model using a technique that's called normal mapping. This requires a bit of explaining, and I would like to discuss that in the next episode. I hope there was something new for you to learn and that you enjoyed watching this video. As always, thank you for joining me, and I'll see you next time. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub, so you don't have to type everything over from the video. Plus, there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering!